So I left this whole thing with the uncomputation. I did a bit of quantum volume in the previous video, but it was still bothering me basically this part here. Because I'm always under the assumption that if you measure the ancilla qubit to be zero, then you really shouldn't get the proper results, right? Because why? Because I mean, why wouldn't you get the proper results? Mm, mm. Nevertheless, ah, hmm, because that's what it's my intuition is failing at that point, and but it's bothering me. So if we've got these, right? Say, uh, so say this is the ancilla qubit, the last one here, and so you then do these. Uh, mm, 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 mm. This ancilla qubit, this, and these. As this being your target. Mm. And so if I do plus, plus, and plus, so those are, I think I was doing it this way. It's easier to see. Yeah, so this is the target, and these are the three inputs. Oh, sorry, where am I? Yeah, exactly. Because we're creating a, yeah, so for all these, so this is the one where this is 1. And the target is 0, right? But when the target is 1, it's only when everything is 1, right? So if I am pos-selecting on 0 here, then I lose. I have the impression I did something wrong last time. I'll probably have to check the video and query, I'd say. But I mean, if you pos-select on 0, you basically the remaining state you have is still valid. What I was doing wrong in the other video, give me a second. So if I go to YouTube and I go to my channel and I go to videos and I go to this part. So let me look for Now what am I doing here? So mm, so that's basically the same that I'm doing. Okay, no, but to the top. Mm, as I'm looking, I'm ignoring the ancilla qubit. I wanted to pause select. I want to see where I pause select it. Mm, because what? Because why am I pause selecting for one though? Uh, why was pause selecting for one? Um, mm, 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 mm. Hmm. Not here. Sorry, in the ancilla qubit. Ah, now I get it. So I pause select for one, for zero. Yeah. Uh, if I pause select for zero, then I'm basically losing the valid state. Whereas if I uncompute, I feel I have to repeat the whole thing. And I pause select for zero, then I keep the valid state. Yeah, that's the point. If I uncompute, if I don't uncompute, I kind of lose the valid state. The reason being that, well, I can't. Yeah, it's entangled. So, okay. So I'm trying to reproduce this here. I'm trying to reproduce this here uh, by measuring these and kind of realizing that, for example, this this amplitude shouldn't exist, right? Because if I measure this to be 0, then I shouldn't, sorry, this one. Yeah, this one is this one. So if I measure this to be 0, then the TOEFL shouldn't have worked at all. But I do get it there. And I fear this is because of the fact that the IBM-Q puts all the measurements at the very end. But isn't this then against the deferred measurement? The deferred measurement problem? I mean, this shouldn't work. If the ancilla qubit is 0, it cannot be that the other qubits are 1. So I'm definitely talking about the whole circuit in here. So zero, 1 to 3. This is ancilla qubit. That really shouldn't work. Maybe I'll try this transpiling stuff, see if I can verify whether the measurements get all put at the end, but it's still, the combination shouldn't be possible. That's what's bothering me right now. There shouldn't be any amplitude in here. Any. Like if I would keep that, there shouldn't be any, because even like this is, you just don't have that amplitude anywhere. You see, it's not, this amplitude is not anywhere. Oh God. How can I figure this out? So for me, I think this, I believe this output, this amplitude shouldn't exist. Nevertheless, it does. So let's run all this stuff again. Doing working on the simulator right now. Yeah. So. The Perlin simulator hist. That's what I want to print. And see these here. This is what's disturbing me. Pay attention that I've added one more classical beat just to have that extra 0 in between. I was just want to make sure that I was the right thing, but I can probably remove that. Maybe because I'm iterating multiple times, that unconsciously tangles and untangles this thing. Maybe. So what if I just run it once? Let's say I just want to run the circuit once. No, I mean not the circuit once. What I mean is the combination of the oracle and the amplitude amplification. So if I do oracle, harmonic oracle, amplitude amplification, and then already go to measurements. So what do I get in this case? Ah, now. Cool. But see, that's interesting. Wow. Yeah, that's definitely interesting. But if you execute that multiple times, then it just works, because the fact that you're running the and let's confirm let's see if what happens if we don't measure the ancilla qubit, right? So we're not measuring the ancilla qubit at all. That calms me down. Okay, cool, because it means if you don't measure the ancilla qubit, yeah, okay. I mean, it doesn't work as it doesn't work really nicely, but it does have a bit the shape that we want, right? But it doesn't work really nicely because we're just doing one iteration. Um, but the point here, my point here is if we measure this circuit, no, if we measure this ancilla qubit, my point here is now we get really different. But there's still a probability of these. That's what I don't get. That's what I don't get. That's really something that I don't get. But there's a really big difference between those two results, right? Maybe that's really what's happening here. What if I add the uncompute step right now? So what if I add that last piece in here? So now I'm uncomputing. I'd like to see a substantial difference now. It works. Huh. It works. Yeah. It works. It works. Cool. So I think uh, that that this has been now understood. So the problem that I was what I was not seeing is that because I was executing the oracle and amplitude amplification multiple times, the ancilla qubit was being unconsciously uncomputed because I might even have been doing this so you've got these in here, and then these uncomputes it, and this computes it again. What if I remove these? And so let me check that again. So now it's messed up. What if I just do one more step? Now that should be... Interesting. Okay. Doesn't work either. It doesn't work either. But as soon as I add another layer, then now it works. I am a bit. So it definitely, when I just have one layer, I see a difference between uncomputing and not uncomputing. So I'm happy with this. But it's funny that if I keep adding these things, then it kind of seems to work or not. What happens if I duplicate these, right? So let's say I'll basically make a gate out of that, and I'll call it TT. And so if I do that again, what's the expected behavior? It's the behavior of a Toffoli. And without that, that's funny. So I was really lucky because I randomly picked three layers, and but if I had chosen an even number of layers, it seems like it's not working. What's more, the more I stack these things, the messier it gets. What? Huh. Until I've done this. So this is 1, 2, 3, 4, 5 layers, and now I'm back to the original layer. And this is all because I haven't uncomputed. Oh, sorry. And this is all because I haven't uncomputed. So because so I've got these here basically, right? So the problem now is if I try to use the ancilla qubit again. So what have we got here? So these are all the invalid ones. This is also an invalid, not invalid, a valid, but like with a target 0. And here we got all ones, right? But if we measure the ancilla qubit to be 0, then we just don't have anything valid anymore. Now, if I start doing this again, right? If I now start doing another Toffoli, so what first of all, what do you expect with a Toffelis? Let's just start. Let's just do this. So let's just do this. I'll do it this way, so I have a similar shape. Sorry, so it should be like this, right? So I got a similar shape in here, right? I can compare The only difference is these things have been shifted because of the ancilla qubit. No? 0. Exactly. Because in this case, we got an ancilla qubit that adds that part here. So what happens if I wanna, how does this look like? Okay, that's yeah, but that's expected behavior. Is it? If it's all zeros, it's fine, but if now you've got all ones, then you've kind of negated that again, right? So, and here, now you're back at the same spot, right? So you can keep doing like that. So you're toggling these behavior. Now, the problem here is if you don't uncompute, that doesn't seem to happen. So, so if I use now, what I would expect here is I would expect that basically with a TT, so that's my target. I would expect this guy to be here, honestly. Yeah. Right? If I uncompute, that's what I should see. What? Yeah. No, that's what I would expect exactly. Yeah. Because here you expect that for the 3 rightmost qubits are 1, the fourth qubit should be then 0, right? That's the, for everything else is stays the same. But if I don't uncompute, I stay with the 3 qubits being 1, so that doesn't work. That doesn't work as expected because of the ancilla qubit. Why? Because basically that step you're doing here just kind of count as an uncomputation. And so now, if now I do what is the change here? There's no change. There's absolutely no change because there's no such state where like that doesn't apply because there's no such available amplitude here where we've got like a 101 because the ancilla qubit would have to be 1. But it's not. But it's not because we've kind of uncomputed in here. Yeah. So that's funny things with the uncomputation. So this is a must actually. I was really lucky that this is working at all. That this was working at all because and as I said, probably after the third iteration, yeah, then you get what you want. But that's just pure luck. You see, so after the third layer, you get what you want, and that's why I was experiencing the same as in my circuit works for. and and so let's take a look at why this happens again. So now Now I'm here, right? And now I know that this hasn't really worked, right? This means I got kind of got the same it works because it works because the second step, it actually acts like an uncomputation, because that's basically not taking any effect. So it's the same as if I uncomputed, and so now I add the same, and so now it behaves like expected. That's why when you have an odd number of layers for the non-uncomputed TOEFL, not TOEFL, the multi-control gate, then it works. Wow. I was just lucky. I was damn lucky. So, lesson learned, please always uncompute. Always uncompute. Now, when I uncompute, still bothers me that I see these, so this shouldn't be. When you uncompute, it works. But if you don't uncompute and you have like an even number of layers in here, then good luck, because it's not going to work. Completely messed up. This does indeed still bother me. That this is a possible solution at all. 0 with all ones. That this is a possible solution. I mean, no, I just see that, yeah, I mean, I just proved that you can have that, right? Because basically when you're adding that second, you're kind of uncomputing. So yeah, that's possible. That's this one here. So, oh, okay, interesting. So intuitively, that's what's happening here. Basically, the second time you apply the amplitude amplification, you're literally uncomputing it. Ah. So that's why in the paper they just run once and it already works. Cool. It even works better with just one step, literally. Right? Because now I've got, all these are 0.08, and if I, yeah, these are 0.06, so that works even better with uncomputing. Yeah, so maybe, so I was just being damn unlucky. I was just being damn lucky. I was being so lucky because I just basically did the 3 layers. And so it's the same, like if one was literally an uncomputation, and so I was doing 2 layers. Oh, so maybe now, okay, so maybe now I will get better results for this computer. We can try, but I probably want to uncompute then the stuff here. So what do they use? They use Valence, they use Orense, and I should have, I think that if I take a look at the IBM Q experience, Sorry, I was paused. Now I realized. I just basically queued it. I was checking the rest of the notebook, see if I did have to uncomment anything else. And let's see if I get any better results. But I'm not. I wouldn't expect like a big improvement here, to be honest. Still cute. I'll pause for now until it's ready. So the job is done. Now let's take a look at the results. Ah, not good either. Anyway, even after some error correction and stuff, I think it won't make a big difference. It's gonna now execute these against against the backend. Okay, forget it. It's not worth waiting. Anyway, yeah, I did learn something useful. I mean, I knew about that computation, but it was not obvious to me here why it was needed. But now I realized that, yeah, well, it's kind of actually needed. I was just really lucky that I used 3 layers. And so the layer in the middle was literally uncomputing the results. Cool, perfect. I think we're almost. I think I'm kind of. I'm feeling like, kind of done with the paper. There's one last thing that I want to check, which will be the next video, which will be the last video probably, which is the not like the other type of graphs. So for the other, because this is a really optimized Oracle with the with virtual vertex technique, but then there's this part here also that I kind of left, I think, open with a KAK decomposition, and I think that's something that I want to take a look into this, just because I don't feel like leaving something open like this. But I think the rest, I feel pretty happy with the coverage of the paper. So maybe I'll take a look at these as well. The way these performances are analyzed is just interesting, I guess, to know, because they are using the density matrix. So this is one thing. I'm not sure how I'm gonna plot these though. And the rest, I think we're good to go. We're good to. It's not good to go, but we're like good to go through the conclusions and then call it a review. I think call it a day. Perfect. Perfect.